In part 2 of this video, we're going to use equations 2.5 and 2.6 from part 1. So if you recall the equations here for this one with this one here and then this one here, and if you recall from the original Laplace transformation equation, so the Laplace transformation effectively for a first derivative, second derivative, and just a y of x here just becoming capital Y of s. So if we undertake the Laplace transformation initially, because this is the stage that we do before we go into the transfer function form, what we're going to do here is, well, that's effectively there, the product of undertaking the Laplace transformation, because here you can see theta double dot, in this case it's y double dot, effectively becomes s squared theta s. So s squared theta s, there you can see that there. Obviously we've got this j here, plus b, so the b is just going to stay there. And then this theta dot is effectively, okay, it's just slightly different notation here, it's y dot, that'll become s. And then in our case, it's not y, it's theta s. Okay, because obviously here you can see we've got theta here of s is common, and also here you see s squared and s. What we can do is we can move s theta s outside, and then just have js, because obviously s multiplied by s is going to be s squared. And then that is obviously equal to, here you can see this final part here, k subscript t, and then lowercase I of t, where if you remember the Laplace transformation of y of t in this case, where y in this case is I, just becomes y of s in the case of y, but in our case here it's going to become I of s, as you can see here. So that's the equation there that we're going to use. So then let's move on to the second one here, so this one here. So here you can see it's slightly different notation. You can see you can use different notations, but d over dt is effectively just your first derivative. So it's the same as y dot. So y dot of x is effectively going to become sy of s. Here I should say actually these are x's here, but these in the previous notation you've seen these are t's. But again, don't get too worried about that. So you can see here L here, and it's going to become S, and because here we've got I of t, this becomes capital I of s. And then plus R I of t, where I here becomes capital I of s. Right, and then here V of t becomes V of s, and then take away k subscript e, and then here you've got this theta dot, where theta dot just becomes sy of s. So s, well in our case s theta of s, so you can see there. Because in this case again, I of s is common, so you can see I of s here and I of s here. So what we can do is create brackets and put I of s outside the brackets, and then just put L of s plus r. And then that's equal then to that term that we just derived. So that's equations 2.7 and 2.8. Again, I just want to refer these here really t rather than x, but again, don't get too worried about that. It's like a typo really, I should have put t's there. So equation 2.7, what I'm going to do now is rearrange that to make the I of s the subject. So you can see I of s here, so I've effectively just divided this equation by k of t, so to give me equation 2.9. What I'm going to do then is substitute equation 2.9, so the equation that we've just derived for the current, I'm going to substitute that into equation 2.8. So in equation 2.8, you can see here it's effectively going to be substituted in here. So what it's going to be is this substituting here, so it's just going to become ls plus r here, multiplied by the numerator of this, and then over k subscript t. And then you can see what I've also done is rearrange it. So I've effectively just subtracted this over here, so that's why I've got x v of s, sorry, take away then this here, take away this, and then equal to 0. So I've just subtracted that and moved it to the other side. If we make then v of s the subject of the equation, so all I've done effectively here is just basically just move this over to the other side of the equation, and then move this up to the other side of the equation. So Vs is the subject. And then because s, theta of s, is common here, what we can do is just move this outside of the brackets given by this. And then finally, the thing that we're going to do in SI units, what we're going to say is k subscript t is equal to k subscript e. Therefore, we're going to effectively say that k is equal to k subscript t is equal to k subscript e, and multiply across by k. So if we multiply across by k, what it's going to do is then give us this relationship here. So we've got that plus k squared and then over k. So this is given by equation 212. Then if we're looking at equation 212 here, so just so you've got that there for your memory. So what we're going to do is just rearrange that to effectively put it into this form. So all I've effectively done is just divide 3 by theta s, so then theta s just becomes here as given here, and then just multiply the numerator of this equation by the s. So you can see the numerator by the s, and that comes there. Because if you recall, we want transfer function to be in the form of output over input, and at the moment this is in the form of output over input. What we're effectively going to do is just flip this equation. So just flip it over so that it's in the corresponding correct form, so output over input. So that then is just equal to k over, then you can see this term down here, and the units for that is radians per volt. So if this was subject to an applied voltage or like a step input without load, the above describes the angle or the angular output. So the angle output of the particular DC motor, or the angular output. So if we were interested in looking at the angular velocity output, what we would effectively do is, what we want is just this here to be s over theta s. So what we can do effectively is we can just multiply by s. So if we multiply this equation by s, obviously what then we end up with is s theta s on the top here, which is your angular velocity, and obviously then the s that was given here originally would cancel with the s if you multiplied it by the numerator, and then that would be radians a second per volt. So that there is your angular velocity. So these two equations are very, very important, because this equation here is for the angular output or the angle output, and this one here is for your angular velocity. So in summary, you should now be able to, based on the two parts of the videos, you should understand how a DC motor, so a high fidelity model, or your differential equation, is derived. So based on looking at the electrical component and the mechanical component, then undertaking the Laplace transformation, substituting the equations to form one equation, and then algebraically manipulate them, because once you've undertaken the Laplace transformation, we can algebraically manipulate the equation to put it into transfer function form. And we've seen the various transfer function forms, so we've seen the one for the angular velocity, and we've also seen the form for the if we're just looking at the angle. So I hope this video has been useful. If you have any questions, please feel free to contact me. Thank you.